So now that we've defined our model architecture, we can go ahead and load our data and then train it. For this section, we're going to be focusing on data loaders and how we can do data pre-processing in PyTorch. So as with all machine learning models, in neural networks, you also have to do data pre-processing, and that is a very critical step. There are a lot of functions that you can use, but generally speaking, we're going to cover two very basic ones that you're going to see very commonly across any kind of deep learning task. And the first is normalization and feature scaling, which essentially means that we're going to take all our features and scale it down to a fixed range, right? So in the case of normalization, this usually means like data that has zero mean and a standard deviation slash variance of 1. Feature scaling sometimes can mean, the scaling your values down to a value between 0 and 1, on the other hand. So both of these sort of methods help you basically standardize the range of our feature values, and it's critical to help our model optimize better. Another sort of data preprocessing function that we commonly use is to convert our data to tensor, especially if your input is an image, right? Which is our case with the digit classification task. It is necessary to convert our image to some kind of tensor representation. And a tensor in this case is a special type of array that is optimized for deep learning applications. Conveniently in PyTorch, we can create a funnel for all of these kind of data preprocessing functions with the compose function, where essentially we can stack data preprocessing functions on top of each other, and transformations will be applied in the order they're found in the list that we input to the function. So we're going to quickly do this. We're going to go to task 1 from the workbook that we worked on before, and essentially build this data preprocessing pipeline using the compose function. So I'm going to give you guys 2 minutes to do that, and afterwards, feel free to resume the video, and we'll go over the solution. Okay, let's go over the solution. So this is task 1, and as we saw in the documentation here, transform takes a list of transform objects. So our input would be a list, and the order in which we want to apply these transformations is we want to first convert the image to a tensor, and there's a toTensor function in PyTorch that we've already imported. And then we want to normalize the value. And as you can see from the documentation here, normalize takes 2 inputs, right? The mean and the standard deviation. And in our case, we're going to provide you the mean and the standard deviation of the MNIST dataset. But in practice, you should be able to basically calculate this mean and standard deviation yourself. And one thing to note is that the length of the tuples that are going to be input to mean and standard deviation depends on the number of channels in your input, right? So in our case, we have a grayscale image, so we're going to have 1 channel. That's the reason why each of these tuples only have 1 value. But if you're working with an RGB image, right, like a color image, there'll be, for example, like 3 channels. So that's one thing to keep in mind. And when you calculate the mean and standard deviation of your input data, you want to do it per channel, essentially. We're going to copy this list of transform functions for our test data set as well, and then run it. I see. Need to rerun the notebook. So awesome. Okay. After you define your pre-processing functions, PyTorch makes it pretty simple for you to essentially use that while you load the data, right? So the MNIST dataset is a very popular dataset, and as a result, it's already built into the PyTorch library. So you can simply load the MNIST dataset with the MNIST function and class, and within this configuration, you can essentially input a transforms object, right? Where you're essentially applying the train transform compose pipeline while you load the data, right? So your data set is going to be loaded with these processing functions already applied to it. Let's run that. And it's going to take a little while for Let me just make sure that the data is actually loaded. Okay, I think it did, although there's some weird error messages. It should have been fine. Cool. So so now that sort of goes over the loading of our data. Another concept that we should sort of go over during the section is the concept of batch sizes. And the motivation behind using batch sizes is that evaluating the loss and gradient over our entire data set every time we want to update our parameters is a very expensive procedure. So imagine you have a data set of like tens and thousands of rows. If you want to compute the gradient over each of these samples every time you want to update the network parameters, you can imagine that that becomes a very, computationally burdensome task. So as a solution to this, we can instead evaluate the loss and gradient over a smaller batch and a smaller subset of our data set. And this generally leads to faster but more erratic steps towards the global minimum of our loss function. So to sort of highlight this, batch gradient descent is essentially gradient descent over the entire data set. And you can see that every time we're updating the network parameters, we're taking the ideal step towards the minimum, right, of our loss function. When you use mini batch gradient descent, where essentially you're using a subset n of your data set, you can see that we're taking a slightly more erratic steps, right? Stochastic gradient descent is when you're essentially computing the gradient and updating your parameters over every single sample in your data set. So you're going to calculate loss and gradient over one sample before updating the parameters. And you can see that this is even more erratic in nature. And this is essentially sort of a trade-off that you should decide based on how much computational power you have, right? Based on the size of the model, as well as the amount of GPU space that you have. Or if you're using CPU, then you're really resource constrained. And based on all of these factors, you should decide, okay, what is an optimal batch size where I can sort of balance the trade-off between having an optimal step towards the loss function's minimum versus having faster, more computationally efficient steps. So sort of continuing on this trajectory, batch size, as I mentioned, is the number of samples we evaluate before updating the parameters. And this concept has some other terminology that we should be well aware of in deep learning. One is iteration, right? And this is the number of times we update the parameters for every pass through the data set. So if we have a data set of 1,000 rows, we can use a batch size of 100, right? Which means we're evaluating the output and loss function for 100 rows or data points before we update the parameters. That will mean that we have 10 iterations because 10 iterations will get us through one pass of this entire data set. There's also epochs, which is the number of times we cycle through the entire data set during a model training, right? So one iteration or going through the entire data set once is equivalent to training your model for one epoch. And usually when you train your deep learning model, you configure by yourself the number of epochs you want to train your model for, right? And this sort of sets an upper limit on how long your model trains for. So with this in mind, we're going to practice loading our data. In our case, the MNIST data set, which is included PyTorch. We actually did the first step already. So the key sort of task here is to go back to our notebook and create a data loader object, which essentially allows us to automatically generate batches of batch size to feed to our model during model training. So you can see that batch size is one of the parameters here. So this is pretty straightforward. So I'm just going to go over the solution right away. So in our case, we're going to define a batch size of 64, right? And then to our data loader, we need to input our data set, which for the train data loader is going to be our train set. With the batch size of train batch size. There's a few other parameters here. There's shuffle. And essentially what shuffle indicates is whether you want to shuffle your data set after every epoch, right? So after one pass through your data set, you want to sort of shuffle your data so that you're basically using a new subset of batch size samples every time you go through the entire data set. Generally speaking, I believe this is good practice. Not 100% sure. In our case, we're just going to set it to true. We can do the same, and I'll let autocomplete this. All right, we can do this for our validation data set too. And by loading this, we have an object that allows us to basically automatically generate batches of 64 samples from our data set, which we've already applied our pre-processing functions for. So that sort of helps you prepare your data for model training. And in the next section, we're going to actually go into the inner workings of how a neural network will learn. Right now, we understand what the neural network architecture is. We understand how an input is mapped to an output. But now we need to understand, okay, based on the output and the loss function, how are we going to update the parameters to a neural network? See you then.